So now we'll cover the very last one, absolute exercise. Relative means same intensity. Absolute is the same workload. So an example of absolute would be, say I go out and run a 6-minute mile. I'm in decent shape because I can run a 6-minute mile, yet a 6-minute mile for me is pretty much going all out, 100% maximal, legs feeling heavy, panting, fading, dying, I pass out at the end, whatever. But I run a 6-minute mile. And then say I'm like, oh wait, this sucks, I'm out of shape. And I feel pathetic and everything, so I decide to go do something about it. And I decide to train and see how easy I can make it to run a 6-minute mile because I want to make it look effortless. So I train for 6 months. And I want to make this same intensity look effortless. So after 6 months, I go and run a 6-minute mile again, and yes, it is effortless. It's much easier now because I'm in much better shape. So that same 6-minute mile, that same workload is much easier. So how do all these values change? So you can guess, heart rate will be lower. Heart rate is lower because it's easier. So it's the same it's the same workload. It's not the same intensity. It's the same workload because it's still a 6-minute mile, but I'm in much better shape after training. So my heart doesn't have to work as hard to do the same 6-minute mile. So my heart actually beats less. It's a less intensity. My heart's stronger. My body's stronger. My heart is more efficient, so it doesn't have to beat as much. Now, if my stroke volumes, my heart rate is decreasing, my stroke volume is increasing. Because it's true, my heart is beating less. It's working less harder, or I don't know if that's a word, but it's not working as hard. The 6 miles is easier, so my heart beats less. Now, if my stroke volume didn't increase, that means I'm not getting stronger. Exercise will be hard, just as hard. If my stroke volume wasn't increasing, if my heart rate was decreasing. So my stroke volume must have to increase because the exercise is easier now to make up for that decrease in heart rate. Now cardiac output remains the same because it's the same workload. It's still a 6-minute mile, so I still have the same volume of blood circulating in my body. So it's still pumping out the same amount of blood, but it's easier because my heart is beating less, so I perceive it as easier, even though it's the same intensity. It's the same workload, and my cardiac output is the same. Again, you can break this into the formula: heart rate times stroke volume. If heart rate is decreasing and stroke volume is increasing, cardiac output is the same. Now, by this point, you should know all the formulas. So VO2 is remaining the same also. Because again, cardiac output is the same, so VO2 is the same because it's the same exact effort. It's still a 6-minute mile, you're just in better shape, so your heart beats less, but it's still the same effort. It's true your VO2 is probably higher after training for 6 months, because remember, relative, your VO2 does get higher after training, but you're still working out at the same intensity, a 6-minute mile, so your VO2 doesn't have any reason to increase at the same workload. And then mean arterial pressure, just like everything else, stays the same. Rate pressure product, you can tell what happens. It decreases. It's kind of like the stress on the heart, indirect measure. If heart rate is decreasing, your heart is working less, so the rate pressure product is less. The stress on your heart is less. Heart rate times systolic blood pressure, 100. And it says parasympathetic and sympathetic. No one cares what they do, they remain the same. So again, let's put this into easy terms to see. Absolute, put in some numbers. So let's say, again, I run a 6-minute mile. 6-minute mile for me is like maximal exercise, legs dying, I'm about to pass out. It's extremely tough, hard for me to do a 6-minute mile. I finish this mile, I definitely cannot do another mile or any more exercise, I'm done. So I run my 6-minute mile. Now that 6-minute mile, my heart rate was probably, just to pick a number, let's say I reached 190 beats per minute, which is almost your max heart rate. I'm not sure what my max heart rate is, but it's 190 is pretty much up there. That's pretty intense. It's either 90% or 100% on max heart rate. So it's pretty damn intense. And let's say my let's pick some numbers. Let's say my cardiac output reaches 21 liters per minute, just picking some numbers. So that's how much blood I had circulating in my body at maximal exercise when I was running the 6-minute mile. And let's say my stroke volume was 120 milliliters. I just picked a random ass number. I don't know if that math adds up right there. 120 times 120, 190 times 120 equals 21. I don't know, but I'm just picking some numbers. And then say my VO2 was like 50 at my max, or when I'm running that 6-minute mile. Now say I train, I run a 6-minute mile again. How would everything change? Well, now that 6-minute mile, my heart has to work less in order to run the same 6-minute mile. So now my heart rate, let's say, is 175. So my heart rate decreased. My heart has to doesn't have to work as hard to do that same 6-minute mile. My heart is stronger. Since my heart rate decreased, my stroke volume increased to like 170. Reason being, if my heart rate decreased, if my stroke volume remained the same, that's not good. That means my cardiac output decreased, and that means I wouldn't be in better shape. If my stroke volume decreased also, that's not good at all. That's never good. But my stroke volume increased to make up for that decrease in heart rate. So this guy decreased, but this guy increased. Now, since heart rate decreased and stroke volume increased, my cardiac output is the same. My cardiac output is still 21 liters at the same intensity. Now my max cardiac output is probably now like 25 liters now because my heart is stronger. But at the same intensity, that same 6-minute mile, my body has no reason to use more blood. It's just like when you take an untrained athlete and a trained athlete at rest, they have the same cardiac output because the body needs the same amount of blood to supply the intensity of rest. It's the same thing here. You're running a 6-minute mile, your body needs the same amount of blood to supply the muscles the same exact way. Your heart's stronger, but you still need the same amount of blood. Now my VO2 also be the same since my cardiac output is the same, and that's really it. My rate pressure product will be less, my heart will be working less, so the stress on my heart or how much oxygen my heart is using will be less because it's beating less. So these are some actual real numbers to do. And you can actually test this, go out and run like a 6-minute mile or a 10-minute mile or whatever the hell is in your fitness, who cares, just go out and run it. And then measure your heart rate when you finish, or wear a heart rate monitor, train for like 2 months or something, go run that same, let's say you run a 7-minute mile. Go run a 7-minute mile, wear a heart rate monitor, record your heart rate, and then train for 6 months, run a 7-minute mile again. That 7-minute mile probably is going to be effortless and you'll be like jogging it. But you run some 7-mile again, wear a heart rate monitor also, your heart rate your heart rate will be less because your heart will be working less because you'll be in much better shape. You can't really measure stroke volume, you can't really measure cardiac output, you can't really measure these values unless you hook up to a treadmill. But if your heart rate is less, you can plug in all the numbers. So we went over relative exercise, same intensity, same percent of VO2, your body perceives it as the same, thus your heart rate will be the same after training. Stroke volume will increase since your heart rate perceives it the same. We went over absolute, which means the same workload, 6-minute mile. We went over maximal exercise. Take an unfit athlete at maximal exercise and a fit athlete at maximal. How do the values change? We went over what happens when you first start exercising. Remember, we all know your heart rate increases, your stroke volume increases, your cardiac output increases, your VO2 increases. It's very important to remember your heart rate increases because first, I guess we'll clear on a new screen. But first, your parasympathetic decreases in order to raise your heart rate to 100, because remember your SA node beats at 6,200 beats per minute. Then your sympathetic increases to take over your heart rate, increase your heart rate even more, past 100. So it's very important to realize your sympathetic decreases first, and then your parasympathetic decreases, then your sympathetic increases. This is synonymous with acetylcholine and vagal nerve, vagal tone, whatever you want to call it. This is synonymous with norepinephrine. And again, beautiful heart rate drill. Since this whole first test was about the heart. And now the next videos will be on, or the next sections of videos I'll do will be all on EKGs, how to read EKGs, how to do mean axis deviation, diagnose left ventricular hypertrophy, right ventricular hypertrophy, diagnose any electrical disorder on the heart, on the EKG. So you can tell when someone's having a heart attack, when the electrical signal is weak. During an EKG, you can't tell the mechanical efficiency of a heart, you can just tell the electrical stimulation. Because the EKG only measures the electrical impulse. It doesn't measure how well your heart is beating or how strong your heart is. It just measures how strong the intensity is. So the next videos will all be over EKGs. And then we'll get to arrhythmias on EKGs, going over the arrhythmias and all that good stuff.